So, please introduce our next speaker, Andreas, who is currently with Movement Labs. So, before Andreas moved to the blockchain space, he completed his PhD at the University of Sheffield in the area of electrical engineering, and later on he joined the blockchain space where he has gone through various companies and different roles. So he definitely has a large experience that he can share with us when it comes to the design of decentralized solutions and activities of blockchain. And today's talk will be presenting his latest activity regarding interoperability and cross-chain settling between different blockchains. With that, I will hand over to Andreas.
Thanks for that fantastic introduction. So yeah, as already said, I'm talking about the secure blockchain interoperability in shared sequencing. And so I'm from Movement Labs, and our goal is to bring Move to the Ethereum ecosystem, where Move is like a smart contract programming language that has increased guarantees on safety and correctness of transactions, and it comes with formal verification support and bytecode runtime verification support. And so Move, the Move language is originally from the project D and Libra, where that also has spawned off Aptos and Sui, so they are also having an implementation of the Move VM. And so in our setting, we also implement the Move VM. And one advantage of the Move VM is that it has a parallel execution engine, so it has a very enhanced transaction throughput and is suitable for scalability. And the way we design it is we want to also, as we are going to the Ethereum ecosystem, provide support for EVM transactions. So we have some interpretation of EVM transactions as well as Move VM transactions to provide seamless integration. We then use this component, which is called the Move executor, in the context of Move rollup framework. And in this Move rollup framework, we have adapters where you can plug in different types of sequences and settlement mechanisms or data readability. So you have a very customizable approach to rollups and different types of settlement mechanisms. We can then use these rollups and these adapters to adapt to provide connections to the rest of the infrastructure that we provide, which is decentralized shared sequences and attesters that execute the blocks and provide execution guarantees and the finality on those blocks. And so the goal of this entire adventure here is to provide interoperability between the movement stack chains that can be created from this Move rollup blueprints that I just showed you before. So I will talk about sequence and execution a little bit now. So here is a rollup design, and our main goal is to separate the sequencer design from the execution. So the sequencer is state unaware, whereas the executor is fully aware of the state and is executing that. And so it's a separation of concerns, and this is something that we would like to follow. One thing that the sequencer can do then is to also become a shared sequencer. And so the shared sequencer serves multiple chains, and the user injects the transactions to a common mempool. With this shared sequencer, you now have the possibility for atomic cross-chain transactions to facilitate interoperability between the chains. And the goal is then to have actually generic composable atomic actions on multiple chains, which means that either these actions that you would like to have in these atomic transactions are executed on all chains or on none of them. And so there has been a study by UDL from the Imperial College of London on the topic of Bern and Munich bridges, and the implications of that are quite similar to our setting as well. So there is bidirectional implications, and the weakest link in a setting of multiple chains can become a contagion. And so I'll be talking about that in a minute. But I will go first around how these atomic cross-chain transactions are processed. So the user is injecting these transactions in the mempool, and the shared sequencer then assigns the the sub-transactions to the given rollup, and so the chains receive a stream of transactions that they process then. Okay, so then there's actually different types of sequencers. So these sequencers, they can, on the left, the shared sequencer could handle this in different ways, and there's like different implementations in the industry as well. So in essence, I think you can have an execution sequencer which has basically awareness of the state, and it should then only submit valid transactions. But for this, it requires access to the state. And so the problem is that this requires a very sophisticated entity, and this increases decentralization of risks. But what you then have is like actually that you can have, as an execution approach, you can have an optimistic execution. So as soon as you receive your transactions, you can, as a chain, you can apply them directly, and you would hope that the rollbacks are not very frequent, because you could impose some sort of slashing condition on the sequencer if it submits transactions that are actually not executable. But if a rollback does happen, that might slow down the throughput, and it might be expensive to roll that back or infeasible. Without an execution, which is the topic that we are trying to follow, is you require actually frequent synchronization across the chains, but it provides the separation of concerns. Another point is that because you require knowledge about like whether this transaction is final or not, during this time you might have to lock your state, and you might have to over-approximate your transaction outcomes actually. So you have to lock potentially the outcome of the state depending on whether it is successful or not, and make decisions based on that. So, so it introduces additional complexity. And so there has been a survey by Raphael Becchio et al., which discusses that this type of cross-blockchain transactions are only feasible in practice with the participation of a trusted third party. That trusted third party doesn't need to have to be centralized, it can be decentralized. And in fact, we have already a component here now. So we have already the shared sequencer, and we can implement the shared sequencer in a decentralized way. And so we can use this decentralized shared sequencer now as a cross-chain communication protocol to come to agreement about the success or non-success of this type of transactions. So what I mentioned before, these issues that can arrive in our setting, and for that I'm going to show this in form of like a graph. So we have like these nodes here that symbolize the sub-transactions of an atomic cross-chain transaction, and they have the dependencies on each other. So they have an edge that points towards the other transaction. So there's this dependency on this level, but it can also be inherited from other transactions that are normal transactions on that given chain. So you see like on chain B now, the transaction B2 is consuming from the state that has been touched by B1. And this can go on, and this can go cross-chain. So one of the issues now is that, I'm not sure whether everybody can see because of the laptop here, but it says that chain C depends on chain A actually through this chain of dependencies. And so you have to consider this in terms of security as well, because now if you have a chain A with a very low security, well now for these transactions on C, the security depends also on A, although there has not been a direct communication between A and C. Similarly for the liveness, the latency, if, like for example, here we have an example where chain B performs with a reasonable latency for a while, and then at transaction B3, we have some increased latency. And since both chain A and C consume from B3, they inherit now the latency problems there. And this has to be considered when you consider the transaction final. And so A has to actually consider not only C, but also the latency of chain B. So again, we have this contagious effect that should be considered, and that you can model through like a graph framework, I think. So how can you actually soften some of these issues or resolve them even that are created through these dependencies? So we show that. So here's an example of like how you can visualize the effects through like these dependency graphs. So by default, you do not actually have to impose a given order for a chain based on this cross-chain atomic transactions. But as you say, if you do not have certain restrictions, this can actually lead to problems. So here we have like this red arrow, which now means not a dependency, but it means like some sort of like anti-dependency. So like you require that either only A1 or A2 can exist, but not both at the same time. And so if there's no direct order on the cross-atomic transactions across all chains, then you can result in a loop here. And if you follow the path here, it will result either in both those cross transactions to be failed, and like all 4 of the sub-transactions to be failed consequently. Or even if you do not handle this edge case very well, then you might increase your computation to find a solution. And so what you can do is now you can impose like a global order, and then for that you actually remove that problem. So you can use the dependency graph model to like find solutions that are optimize your ordering. So I use this graph here now to go on to actually talk about the cross-chain communication protocol. So the sequencer is handling this communication. And now it has this question that the chain A should report that this transaction failed, but it might be faulty and it might inform the communication protocol that A1 succeeded, and so this is a problem, right? So you have to, so how can you trust actually this outcome? And so suitably we have actually like already a setting here. So in our infrastructure we provide post confirmations, which is like a staked guarantee that, so there's like economical security attached to it to the finality of a given block and possibly to given transactions. So these attesters basically execute for a given rollup the block, and then they provide these guarantees on whether it has been successful or not. And so what we have here now is like we have still this separation of concerns. So we have the attester here who like handle the execution, and this can be parallelized. And then we have the decentralized shared sequencer, which takes care of the ordering. And so this separation is something we could favor. So this is just a post about post confirmations of like when it can happen. In essence, it can happen on layer 2 or layer 1. But if you do it on layer 1, you get additional guarantees around like that you can also slash the network of validators, and so you get actually layer 1 security. So what in essence is the outcome here of these post confirmations? So you have this not quite Ethereum security, but you receive that at a much faster speed. And so this is something that we require for the shared sequencing, because as I said, we want to resolve this at a high speed, right? So here we have this problem that we showed before, and so this is very slow. And what you can do now is, for one, what I showed you before is like you can use maybe this attester network to facilitate faster assurances of when something, whether like a cross-atomic transaction has been successful or not. And you can also do other things. You can introduce timeouts in the shared sequencer as it handles the cross-chain communication. And so you have like multiple ways of reducing these slow chain problems. Right, so I think I might be run out of time, or okay. So then maybe like some additional applications. So we are like in this heterogeneous chain system, and we can use these dependency graph models to optimize our ordering, as I showed you with that first example. And you can use it to better predict finalities and identify the least latency impacting ordering. You can also do consistency management with it, so you inform when you chains, you want to inform each rollup around when actually latency is reached and when transactions are truly final. And you can use the model to have security propagation and vulnerability detection if something happens in one of the chains, and then that information can be propagated to other chains as well. Yeah. And so this is the presentation about cross-settlement.